everyone, welcome to Chem 20. I'll be your professor this semester. My name is Professor Verissimo, and I absolutely love chemistry, and I am super excited to have you in the class. We are going to get started by jumping right into Chapter 1. So let's get going. So just to start off, we're going to talk about why chemists study chemistry in the first place, right? So chemists try and understand how and why changes occur in nature and the human body. So chemistry is kind of in between physics and biology, right? Physics usually will try and explain large phenomenon, right? Whereas biology tries to study things that are very, very small. Chemists kind of bridge these two disciplines and will actually kind of help biology and physics, which is kind of cool. So what we do as chemists is we try and explain the macroscopic world. So the stuff that we can see with our eyes, no microscope, just looking at it normally. And also though, the microscopic world, which is made up of things that are too small to see. So the macroscopic world is usually, like I said, described by physics. In the microscopic world, we think more of biology. And I told you chemists kind of try and bridge those two different disciplines. Okay, most of the time we will spend our time talking about atoms and molecules and how those atoms and molecules respond to or correspond to the macroscopic world, right? Because let's say in lab, even though we're studying atoms and molecules, those are too small to see with our naked eye. And we don't use microscopes like we do in biology. So instead we study experiments that we can see, at a macroscopic level and use that to explain what's happening on a microscopic level. So that's kind of the broad overarching themes of what we do in chemistry. So before we jump right into chem, let's talk a little bit about the scientific method. Likely, if you've had a science class before, whether it was middle school or high school or even, somewhere at college, you've likely talked about the scientific method. The way we talk about it in chemistry may be a little bit different than the way you've talked about it previously. So I'm going to go through that. So the first thing that we do is usually we'll collect some kind of facts and data that are relevant to our question. Okay. A lot of times the way that we do this in chemistry is the first step is actually to perform an experiment. And that may be different than what you've done in biology or in physics. But likely we will perform an experiment first and kind of see what happens, right? And then after we see what happens from our experiment, we'll use that data to look for trends. Does this happen every time we do this experiment? Or are there, different things that happen, right? And so we'll make a hypothesis. So a hypothesis is a tentative explanation of the data that we collected from our experiment. And you always need more experiments to validate your hypothesis, right? Just because we do an experiment and something happens once doesn't mean that it will happen again that same time. So we call this, in chemistry, we call this replicate trials, which means we'll do the same experiment over and over and over. And if we always get the same result, then that means it's a pretty good hypothesis, right? If we get different results every time, then maybe we need to change our hypothesis. Okay, so that, whole series of testing our hypothesis will then, like I said, allow us to modify our hypothesis if we need to. A hypothesis has to explain all of the data, even if there's data we don't like. So if something, goes wrong in our experiment, right, or at least we thought maybe it was wrong, maybe it's telling us that our hypothesis isn't actually very good. So a hypothesis has to explain all of our data. Okay, and once we get a really, really good hypothesis that every single time it always explains what happens in our experiments, then we call this a theory. Okay, so a theory summarizes a hypothesis that's been supported by repeated experimentation. And again, that's really important, repeated experimentation. Okay, and the theory will be valid as long as there's no evidence to disprove it. So that means as long as the theory always explains all of our data, then it's a good theory. Okay, and so this is our example here. So let's say we made some observation. Milkmaids, which we don't really have anymore, but let's say we're studying milkmaids and we notice they're never getting smallpox. Okay, so maybe this was a long time ago. Nobody really gets smallpox these days. But let's say we were looking at milkmaids and we're like, wow, they don't get smallpox. What is special about these milkmaids? Milkmaids actually get cowpox, which is different. Maybe you've never heard of that, but that's okay. So these milkmaids got cowpox, which allowed them to be immune to smallpox because these viruses are kind of similar. So that would be a hypothesis. We're like, wow, okay, all these milkmaids, they all had cowpox. That's what they all have in common. Maybe that means they can't get smallpox. So an experiment, and this is like a don't do this at home, okay? We're gonna expose a healthy child to cowpox and see if they don't get smallpox. Okay, so obviously these days we do not use children in our trials. This is actually an example from your book. I promise I didn't write this, and I'm not advertising that you should go, start exposing children to certain diseases. But let's say we intentionally exposed a healthy child to smallpox, or to cowpox, my apologies. We expose them to cowpox and we see, all right, do they get smallpox? Right? We know that now they've had cowpox. Will they go get smallpox? They're not a milkmaid. So, maybe there was something special about these milkmaids. This child isn't one. So we'll expose them to cowpox and then see if they get smallpox. So if they did get smallpox, we're like, all right, well, that didn't work. Let's make a new hypothesis. But if they didn't get smallpox, then that means that it worked. Because the child didn't get smallpox, it must have meant that the cowpox immunity allowed him to be immune from this smallpox, which would be cool. So that would be, we would need further experimentation because remember, I told you, replicate trials. We can't base what happened in one child and allow that to explain everything. We have to have replicate trials. So we're gonna round up a lot more people that are not milkmaids and we are going to give them cowpox and then see if that makes them immune from smallpox. And if it does, then that means we have a pretty good theory. So you may have heard this, I keep saying theory, and you may have heard people say before, like, oh, that's just a theory, right? Where a theory is, an educated guess, or it's going to explain things, but, it's just a theory, right? In science, a theory means that it's been supported by tons and tons and tons of data, right? We do these experiments over and over and over again and always get this exact same result. That's how we get a theory. It's not just this like random guess that we've made. It's a really, really, really solid idea that's backed up by tons of data. So a theory, right, that I have down here, a theory explains why something happens, or it tries to at least explain why something happens. So in this, we're saying, okay, our observation was that milkmaids didn't get smallpox. So this whole process was trying to explain why these milkmaids don't get smallpox, right? And the conclusion was they don't get smallpox because they already had cowpox. So that's our theory, is that cowpox, or this immunity to cowpox is allowing us immunity to smallpox as well. So a theory explains why something happens. This is different from a scientific law. A scientific law is going to predict what happens. If I throw the ball up, it will come down. Gravity, right? So that we know, if you throw something up, it always comes down. That is what happens. But our theory of gravity explains why that happens. And you can get into lots of that in physics. But I did want to point out that these two terms are different. Scientific laws predict what happens, and a scientific theory explains why it happens. I have this cool video that's been posted in Canvas that will go through, it's only 5 minutes, so it's not going to take a ton of your time, but it will go through the differences between scientific law and scientific theory. But like I said, the gist of it here is that a scientific law predicts what happens, and a theory predicts or explains why it happens. All right, let's get into a little bit more about chemistry. So chemistry is the study of matter and the changes that matter undergoes. So matter is anything that has mass and occupies space. So pretty much everything that you can hold or touch or anything like that, that's matter. Okay, and like I said, chemistry is the study of the changes that it undergoes. So most of the times when we are doing labs, we are going to, pour two things together and look at the changes that happen. That's the cool part of chemistry. Labs really are the best part of this class. So some examples down here. We have in this first photo, this one that's A, that is the gas burner in your home, right? Maybe you're making some pasta and you're going to boil some water. That is a chemical reaction. We've ignited that natural gas that's coming through the lines. And we'll talk more about how we know whether a reaction is happening or not a little bit later in the course. This one down here, B, right directly below it, that is an Alka-Seltzer tablet dissolving in water. That is also a chemical reaction, right? You see those bubbles that are being produced? That is carbon dioxide. So that whole process, the fact that we're seeing those bubbles, that's a chemical reaction too. Here's one up in the top, right? That one is a car rusting. When iron is exposed to oxygen in the air, it has a chemical reaction. It turns red and it rusts. And then down here, D, baking cookies. That's a chemical reaction too, right? We mix all of our ingredients together and we put it in the oven and it allows it to cook. Cooking is a chemical reaction. So all of these things that you're familiar with already are chemistry. Chemistry is all around you. So if you have to take this class for your major and you're like, man, what am I ever going to do with chemistry? Chemistry has nothing to do with my life. It does. Pretty much everything around you is chemistry, which is really cool. So my goal for this class is to show you how chemistry relates to your life and that chemistry is really cool. I love chemistry. I've devoted my life to chemistry, and I wouldn't have done that if it wasn't super awesome. So hopefully by the end of this course, you are going to have at least a little bit of the passion for chemistry that I do. So chemistry deals with the composition, structure, properties, reactions, and energetics of matter. So that's kind of a really broad description. But chemistry is just looking at, like I said, the changes that this matter undergoes. So whether it's big or small, right, matter is pretty much just kind of stuff. Anything you can hold or see or feel, right? We have lots of things that are matter, and so any changes that it undergoes, chemistry. Okay. On the microscopic level though, right, so if we did get out our microscope, all of this matter is composed of these tiny, tiny, tiny fundamental particles, and they are called atoms. We are going to spend a lot of time talking about atoms. And once you get a bunch of atoms together, they make something that you can see, right? So like I said before, the microscopic level, we will use, and that's most of what we'll talk about, to describe things on the macroscopic level. So, atoms. Atoms are the smallest quantity of matter that still retains the properties of matter. And that will make a bit more sense when we start looking at things like protons, neutrons, and electrons a little bit later. But atoms are called the fundamental building blocks of matter. Okay, so you can think about it like this, our atoms, right? Here is a collection of DVDs, and this is the example in your book. I think it's actually getting a little bit outdated because, who really uses DVDs anymore now that we can all stream videos? But if you have a collection of DVDs, right, that can be separated. You can kind of, pull apart all of those DVDs until you have just one. But you can't keep pulling apart the DVD and think that it's still going to work when you want to go play your movie, right? You can separate those 4 DVDs into different ones. They will still play your movies, right? They're all different movies, or the same, whatever floats your boat. But if you broke this DVD and you tried to put it in your DVD player, then it's not going to play your movie. So a DVD is kind of like an atom, right? If we had a collection of atoms, right, we can pull apart these atoms, but once we get to just one atom, that is going to be our fundamental building block of matter. We can still call that an atom, but once we get smaller and smaller, like I said, protons, neutrons, electrons, which we'll talk about later, then it's not an atom anymore, okay? So more on this a bit later. Once you have a bunch of the same type of atom, if you had a bunch of these little atoms and put them together, you get what's called an element, okay? And this element cannot be broken down into simpler substances. So kind of like, let's say you're wearing a ring and it's made of gold, right? You could separate all of those gold atoms, but they're always going to be gold, right? If you separated them, they're not going to magically turn into silver or iron, okay? And so elements are these building blocks of matter. So this term atoms and elements we're kind of going to use interchangeably a bit, okay? Atom is more of a general term where we have lots of different kinds of atoms, and then elements are things like gold or oxygen or helium. Okay? So they're a bit more specific types of atoms. Currently, on the periodic table, we know 118 different elements. Okay, that's actually really exciting. It was fairly recently that the periodic table was updated and quote unquote finished, which as a chemist was really big news and really exciting. And they were recently all got names, which is even cooler. So 88 of these elements out of the 118 are naturally occurring, which means that you can go find them out in nature somewhere. They may be combined with a different element, but you can find them out in nature. Most of them are solids, okay? So things that you can think about like, iron or gold or lead, right? Those are solids. Most of the elements are solids. At room temperature, there are only 2 elements out of these 118. Only 2 elements are liquids, which is kind of cool. One of them is bromine, which you probably won't see. It's kind of like an amber colored liquid. It's kind of a brownish yellow. It's really pretty. And then mercury is also a liquid. We actually have some at COS. So if you ever wanted to see some mercury, it's pretty cool. It's like a shimmery, silvery liquid. Looks really cool. It's really, really deceptively heavy, which I think is one of the coolest things about it. You won't find it out much because it's really toxic. So if you happen to have any mercury at home, please call hazmat as soon as you can and have that picked up. It's bad news. And then at room temperature, 11 of these elements are gases. So hydrogen, nitrogen, oxygen, fluorine. One that you're probably familiar with is helium, right? We blow up these balloons, or you can, inhale it to talk kind of funny. You may also be familiar with neon from neon signs and argon if you do any kind of welding, right? So like I said, 11 of them are gases, 2 of them are liquids, and the rest of them are solids, which is cool. On your periodic table that I have on Canvas and that you will get for all of your quizzes and tests, that's in black and white. But if you go to this website, and I actually have it linked in the Chapter 1 module in Canvas, you can find this interactive periodic table, which is really cool. And that actually has different colors of the elements. So like anything that's black, that's a solid at room temperature. So like, zinc or copper, right? These are all black. If you see one that's in blue, that means it's a liquid at room temperature, like bromine and mercury. And then if it's red, that means it's a gas at room temperature. So like helium, right? We've got some argon, neon, oxygen, all of those. So one of the things I'm going to teach you in this class is how to use your periodic table. Okay? Your periodic table is like the world's greatest cheat sheet, and you're allowed to use it on every quiz and test, which is really cool. Okay? So my job, or one of my jobs, is to teach you how to use this periodic table throughout the course. There is a ton of information stored in here, stuff that's not even like written down. It's based in the way that it's organized and the order and all of that good stuff. Everything on this periodic table means something. So as we go through the course, you're going to find out more and more and more about this periodic table and how cool of a cheat sheet it really is. So one of the things, like I said, are all of these different colors. They are telling you what the different elements are, at their state of matter at room temperature. And so this last one that you're seeing down here, this is unknown. And you might be thinking, well, how could it be unknown? Somebody's studying these elements, right? Like, how do you not know this stuff? Well, the thing is, these ones down here at the bottom, okay, that are in this kind of gray color, the way that they've made these elements is by slamming 2 other elements together at really, really high speeds. And so these elements only existed for like milliseconds at most, right? And so we don't know what state of matter they're in because they didn't exist long enough. Like I told you, this periodic table was recently finished. These ones down here are our newest ones, and they all recently got names, which is super exciting. So now the periodic table looks mostly done, which is pretty cool. But like I said, you're always going to have access to this periodic table on quizzes and tests. Yours will be in black and white, so it doesn't have all of these cool different colors on it. But it's super handy to use this periodic table that I've linked here in the Chapter 1 module when you're working on your homework or working on any lecture worksheets. All right, moving forward a little bit. So these 118 elements, like I said, they are, a lot of them are found in nature, 88 of them, but just 8 of these elements, so 8 out of the 118, make up 99% of the planet's crust, which is crazy, right? So most of the world is these 8 elements, and the other 110, right, are the other 1%, which is kind of crazy. The most abundant element in our crust is oxygen, which you might think is kind of weird. You're like, well, oxygen's a gas. Why is it in the crust, right, which is a solid? It's usually bound to other elements. So it's bound to iron or bound to aluminum, right? It's bonded to those elements. But we also have silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. That is what most of our Earth is made of, which is pretty cool. Oxygen also accounts for about 20% of the atmosphere, which is important because we need it to breathe. It's also found in almost every rock, sand, soil, right? Oxygen is everywhere, which is really cool. In our bodies, right, our tie into biology here, our bodies also have a ton of oxygen, right? Most of that oxygen is bonded to hydrogen in the form of water, but it can be bonded to other things. We also are a lot of carbon. We are an organic, walking, talking collection of molecules, which is pretty cool. And we also have some other things that are present like chromium and copper, but mostly we are carbon, oxygen, and hydrogen. Pretty cool. All right, so let's talk about the names of these elements. A lot of the names are derived from Greek, Latin, or German words that are describing something about the element. For example, iodine, which is cool. We won't actually play with iodine much in this class, but you might if you go on in chemistry. But iodine comes from the Greek word iodis, which means violet-like. And iodine, when it is not a solid, right, when it turns into a gas, it makes a purple gas, which is really cool and really pretty. But they saw this purple gas and they named it iodine to mean violet-like. Okay. Some elements are named for the location of their discovery. So there's an element called germanium, which was discovered in Germany. So they just, they named it germanium. Other elements are named after famous people. So there's an element called curium, which is named after Marie Curie. She is a very important part of chemistry, and you'll learn more about her as you go on in the sciences, but she is pretty cool. But so, in summary, our names for these elements are describing things about their property or about where they were discovered or named after a person, most of the times. So rather than continually writing out the names of these elements over and over and over again, because that would get a little cumbersome, they all have a symbol, an abbreviation. It can either be one letter or 2 letters. So like iodine is I and barium is Ba, right? So 1 letter or 2 letters. So I want you right now to find a periodic table. Any periodic table will do right now. But I would recommend going and printing the one from Canvas, the one that's black and white that you're going to get to use on quizzes and tests. Get familiar with that one, and then use it while you're working on lecture worksheets or homework so you're really familiar with it. But if you haven't done that yet, pause here, go find a periodic table, and unpause once you're ready. All right, hopefully you have a periodic table now. So if you look, find the element that is N, okay? Somewhere, usually below it, it will tell you the name of that element. So the name of that element is nitrogen. Let's do another one. Find this one. All right, so hopefully you found it. Au is gold. Just so you know, like a bit of a spoiler alert, you're going to have to memorize these elements and symbols, the names that go with the symbols. So like you will need to know that N is nitrogen and Au is gold. So the way that I remember Au is gold, because it seems a little bit random, right? It's actually because the Greek name for gold is aurium, A-U-R-I-U-M. So it's abbreviated Au. But I remember, Au, I'm made of gold. And that's how I remember it. So there you are. All right. More on the whole memorization thing in a little bit. The first letter of your symbol always has to be capitalized. So like if we go back and look, when there's only one, that one letter is capitalized. If there's two, then the first letter is capitalized and the second one is lowercase. If you're one of those people that writes in all caps, stop. Okay? Capital letters and lowercase letters in this class mean different things. So if you had written A-U, that is not gold, and you will get marked wrong. If you write A-U, also not gold, you will get marked wrong. The only way to write this is A-U. So don't write in all caps, don't write in all lowercase. The cases of things mean something, so be very careful there. So for an example, if we look up cobalt, so you can find cobalt on your periodic table, it has the element symbol capital C, lowercase o. That's cobalt. If you were one of those people that writes in all caps and you wrote CO with two capital letters, that actually means that there are two different elements bonded together. Capital C means carbon and capital O means oxygen. So this would mean carbon monoxide, which is very, very different than cobalt. Okay, so be very careful. Make sure that you are capitalizing things when they should be and not capitalizing things when they shouldn't be. So here are some other names of elements that are derived. Like you might think they're a little bit weird, like antimony. If you're looking up antimony, you see that its symbol is SB, and you're like, that doesn't make any sense. It has nothing to do with the name. Well, here is a former name that it used to go by, right? And so that makes more sense. You're like, oh, okay, I could see how those go together, but its new name is antimony. Same thing with like copper is Cu, gold, like I said, is aurum, and you know, iron is ferrum, all of those good things. So if you're looking at the elements and you're like, wow, these symbols have absolutely nothing to do with their names, it's because they came from a former name. Usually it's Greek, sometimes it's German, sometimes it's different Russian, sometimes. So there's different things. All right, so on to this, our symbols of the elements, because I alluded to the fact earlier that there's going to be a quiz on this. These are the ones you need to know. So you don't need to go and memorize all of the elements on the periodic table. I have narrowed it down for you. You need to remember these, okay? And so here's, there's 3 different columns that are happening here. This is also in your book, and I've also posted this in Canvas by itself. So you don't need to like pause here and remember all of this. You're welcome to screenshot it though, if you'd like, or take a picture so you don't lose it. But what you need to know is like if I write down aluminum, you write Al. That's it. You don't need to know that aluminum is number 13. You don't need to know that its mass is 26.98. You don't need to know any of that. You just need to know aluminum is Al. Or let's say I wrote K. You would write potassium. That's it. The best way to memorize these is to make flashcards, okay? In this class, we'll do some memorizing. Most of it actually happens at the beginning of the semester. So as we go on in the course, there is less and less memorizing. But there is some upfront, like these elements. Like I said, best way to do this, flashcards. I would recommend making handwritten flashcards. You can find apps and things that have flashcards built into them. But there's been a lot of studies done that show if you write something down with your hand, then you're more likely to remember it because there's a connection to the act of writing it and the way it programs in your brain. So that's my recommendation to you. Obviously, you can use, other flashcards if you like. I don't care how you memorize them, just make it happen. you go ahead and check Canvas to see when that quiz will be for the section of the class that you are in. Okay, check that weekly schedule and it will tell you when that quiz will be. But I wouldn't wait. I would recommend starting right now. Make these flashcards and start working on them. All right, so as we go through these lecture videos, I will embed time to practice because it's a lot of information, right? Especially if you watch this all in one go. There's a lot of information coming at you. So I'll embed these little slides that tell you when you should stop and work on some problems before continuing on with the lecture. Okay, so in Canvas, if you go to the Chapter 1 module, you will find the Chapter 1 lecture worksheet. Okay, these lecture worksheets, I have one for every single chapter in the class, and they are not for points. You will never be turning this in, and honestly, I won't know if you don't do them. But I will tell you, the people who are most successful in this class do these lecture worksheets and then print them out and do them again, because they are helping you to practice all of these skills or all of this information that you're learning in the lectures. Okay, so what I want you to do right now is pause here and go find the Chapter 1 lecture worksheet and do problems number 1 and 2 on that lecture worksheet. Okay, once you're done, come back and then we will keep going. All right, so hopefully you went and you did those problems number 1 and 2 on the Chapter 1 lecture worksheet. Like I said before, those are not for points. The points will actually come from your homework assignments in ALEKS. Okay, I will tell you though, some of those ALEKS problems are pretty tricky. So if you try to just jump into doing the online homework, then usually people spend a lot of time doing it because they get frustrated that they haven't gotten the practice they need in order to be able to do the homework assignment. So the way that I usually recommend this course, watch the lectures and do the lecture worksheets as you go. Once you finish the lecture worksheets, then go do the ALEKS assignments. I promise you it will be much, much easier to do the ALEKS assignments after you've done the lecture worksheets. Remember, my whole goal here is to support you in being successful at learning to do chemistry, okay? So I have designed this course to make it so that you will be the most successful that you can. So take my recommendations, I hope you follow them, and now though, we will move on with Chapter 1. All right, so like I told you earlier, there's a lot of information in the periodic table, right? And I told you one of the things that I'm going to help you do is understand how it's organized and how it's the world's greatest cheat sheet, okay? This periodic table that we use today was designed by Dmitry Mendeleev in 1869, and it organizes the elements based on their properties. Okay, that was actually really revolutionary. I won't go into the whole history of the periodic table, but it's actually pretty cool. But they initially started kind of grouping elements together by ones that behaved the same. And then they ordered it eventually, like we see today, in this kind of staircase method. The ones that go, when they're up and down like this, we call that a group. Okay, up and down there in the group, they have similar properties. Okay, so if they are stacked on top of each other, that means they behave kind of the same way. If you have your periodic table handy, this one on the far right, my apologies, those are the noble gases. And they are called the noble gases because they are all gases, and they also are all unreactive. Okay, so they all ended up in the same column because they have similar properties. And like I said, these columns, they are called groups. The horizontal rows that go left to right, those are called periods. And if you look, those go in increasing order by the number of protons, which we'll talk more about a little bit later. But that number at the top, that is called their atomic number. So left to right, they're in order by atomic number, and up and down, they are grouped with similar properties. Okay, these 8 tall columns, so 1, 2, and then this one, 3, 4, 5, 6, 7, 8, essentially. The ones that have the A's, you can follow those. So those are what's called the representative elements. Okay, those are also called main group elements, and some of these groups have specific names. So again, hopefully earlier you went and printed out that black and white periodic table. Right now what I want you to do is write the names of these groups on that periodic table so that it will help you remember them. Okay, so if you find group 1, call that the alkali metals. And don't write over it like this. You might just kind of do something like this and be like, okay, these are the alkali metals. Okay. And then this one, these are the alkaline earth metals. I'm not going to require you to memorize the names of these, but I do want you to know the halogens and the noble gases. So I want you to know the groups, right? Those 4 different groups and all of their names. These ones here are called the transition metals. Please also label that on your periodic table as well. So these are the names of the different sections of the periodic table that I want you to know. On yours, there's likely some elements down at the bottom, right down here. These you can label as well. We actually won't do much with those, but these are called the inner transition metals. Okay, so you should have labeled on your periodic table the alkali metals, the alkaline earth metals, the halogens, the noble gases, the transition metals, and if you like, you can label the inner transition metals as well. So if you hop over to Canvas, right, in the chapter 1 module, I have a video there and it's really short. It's like 3 minutes. And it's all of the different alkali metals being chucked into water, which is fun. So if we went back a slide, these alkali metals here, again, remember, if they're in a group, that means that they have similar properties. So all of these alkali metals react when you put them in water, which is really cool. They actually kind of light on fire or they explode, which is really fun. As you go down the periodic table, they get more and more and more reactive. So in this video, they start by putting lithium in water, and they go on to potassium and rubidium and cesium, and all of that. They put them into water. It's very, very cool. And it just shows you that all of these alkali metals, because they are in the same column, they all react with water. They react different amounts, but they all react with water because they're all in the same group. Therefore, they have similar properties. All right, another way that we can describe these different types of elements is by metals, nonmetals, and metalloids, okay? So hopefully you have some colored pencils available at home, or maybe you have some crayons laying around, and you can color in that black and white periodic table that you have, okay? What I want you to do is pick one color for the metals, or you can leave them white, and then one color for the metalloids and one color for the nonmetals. And I want you to shade in your periodic table as it's shown here, okay? I do want you to shade lightly. You should still be able to read your periodic table after you're done coloring it. But pick one color for the metals. So these here, in this kind of like, I don't know, light greenish color, those are metals. So whatever color you pick, maybe you picked, I don't know, yellow. I would, make a little box. I would shade it in like yellow, and I would write, okay, this color means metals. And then pick a different color. These over here, these are your nonmetals. Okay, and again, I would pick another color, shade it in, and say, okay, these are the nonmetals. This is what this color means. Oop. And then a third color for these metalloids that are on the zigzag line. Okay, so here they're shown in like a yellow. Like I said, these are metalloids. And I would make, a third box, shade that in, and say those are the metalloids. Okay. All right. So pause here, shade in these colors, and then come back when you are ready to move forward. Before we move forward, sorry, I wanted to mention hydrogen. Make sure you didn't color it the wrong color. Hydrogen is a nonmetal. Okay, so make sure it's the same color as your nonmetals. All right, moving forward. we have a practice problem. So hopefully you have your colored periodic table right in front of you, and I want you to use that periodic table to identify whether these are a metal, a non-metal, or a metalloid. If you didn't go color your periodic table, go do that and then answer this question. All right, so nitrogen is a non-metal, silicon is a metalloid, calcium is a metal, chlorine is a non-metal, and astatine is a metalloid. So hopefully you colored everything the right color and we can roll on. All right, so the reason we care about whether these elements are metals, non-metals, or metalloids is, again, they're telling you information about these elements, right? Again, I told you the periodic table has a ton of information. It's a great cheat sheet. So anything that is a metal, right, are all going to have fairly similar kind of characteristics. Like metals are solids at room temperature. Our only exception there is mercury. All of the other metals are always solid at room temperature. They are also shiny, right? If you think about, I don't know, maybe aluminum, right? Think about aluminum in your head. It's shiny, it's a solid. It's a good conductor of heat and electricity. It's malleable, which means it can be shaped. So we can use our aluminum to make things like aluminum cans. Okay, and it's also ductile, which means it can be drawn into wires. So like the wiring that's in your house, that is usually copper wire. So they took, a piece of copper and they kind of pulled it and made it into wires. Metals also have really high melting points and high densities, which we'll get into density a little bit later. But essentially this really high melting point is the reason that they are solids at room temperature. And some common metals are those that you see below: aluminum, gold, platinum, silver, tin, iron. The list goes on. Some non-metals, right, like the one that's shown up here, if you live in Hanford or, have been to Hanford, you may have noticed, or, mostly I think, that the water has a bit of a different smell or a different taste. That's because the soil in Hanford actually has some sulfur in it. And so that is what you're seeing here in this picture, that kind of yellow rock, that's sulfur. I actually was in Canada and saw this big mine of sulfur, these giant piles of yellow, which is kind of what this guy is doing. Very, very smelly. But metals in general are not shiny. So if you look at this sulfur, it doesn't have that shine that we were seeing with the aluminum. And they are brittle. So if you took one of these and you hit it with a hammer, it would shatter. As opposed to a metal, if you hit it with a hammer, you would be able to pull it into sheets. Metals, or non-metals, my apologies, have fairly low melting points and densities. So for this reason, they are often not solids at room temperature. Sulfur is, but a lot of these non-metals are gases at room temperature, like oxygen and nitrogen and neon and things like that. They are also poor conductors of heat and electricity. So that means they're usually used as insulators to stop heat and electricity from flowing. So like I said, some common nonmetals, carbon, nitrogen, oxygen, and, like I said, sulfur. The ones that are in between, so if you remember, we had metals kind of on the left-hand side of our periodic table and non-metals on the right-hand side. The ones that are in the middle along that zigzag line are called metalloids, okay? Metalloids are listed here. I won't talk about them all, but those are some metalloids. And the reason that we call them metalloids, and sometimes you'll hear them called like semi-metals, the reason for that is because they have some of the properties of metals and some of the properties of non-metals. Their properties kind of fall in between. So they're better conductors of heat and electricity than those non-metals we were talking about, but they're not as good as our metals. Okay, so they're kind of in between. It's the same kind of thing, like I said, with our electricity, with our heat, all of that, they're just kind of in the middle. So we usually will call them semiconductors because they kind of conduct heat, they kind of conduct electricity. And actually we can change these properties by varying the temperature and the pressure of our conditions. And so we can make them better conductors or worse conductors, which is really cool. If you've ever been to the Bay Area, right, there's a very large area that's known as Silicon Valley. Okay, and Silicon Valley is known for their technology. The reason it's called Silicon Valley, and we think of that with technology, is because they use a lot of silicon, and silicon is a metalloid. Silicon is used in computer chips because it's a semiconductor. So all of those different, aspects of technology are using these computer chips, so that's why we call it Silicon Valley. It literally means there's lots of technology happening around here, which is kind of cool. Okay. So here is a table that's going to compare the different properties of metals, nonmetals, and metalloids. So our examples here are silver as a metal, antimony as a metalloid, and sulfur as a nonmetal. Okay, so if you'll look, those are our examples, and then you'll see the properties being compared. We have our densities there. I told you we talk about density a little bit later, but everything else should be good examples of the properties of each one of those types of elements. All right, so I want you to pause here and do problems numbers 3 through 10 on the Chapter 1 lecture worksheet. So again, like I told you, I'll have these slides embedded regularly throughout the lectures to give you time to practice, to take a brain break, to get a drink of water before continuing on with the lecture. But you are in luck because this is actually the end of our very, very first lecture. So you've made it. You've made it through the first lecture of Chem 20. Congratulations. Make sure, like I said, to go back though and do these problems number 3 through 10 on the Chapter 1 lecture worksheet to practice those properties of metals, nonmetals, and metalloids. So I do want to remind you that I'm always available for questions. Just because you're watching this lecture online doesn't mean that you can't ask me questions. If you have questions, if you get partway through the lecture or at the end of it or while you're working on a lecture worksheet, please, please, please send me questions. I teach chemistry because I love talking about chemistry and because I love helping students understand chemistry. So if you're ever stuck or you're wondering something, please feel free to reach out. I love to answer questions. There is no question that's too silly of a question to ask. Contact me via Remind, via email, through my office hours, whatever way is most convenient for you. Even if it's outside the times that you're like, should I send it, should I not? Go ahead and send it, and likely I will answer. So work on these problems, complete that Chapter 1 lecture worksheet, send me any questions you have, and otherwise, I will talk to you guys next time.